So we are very pleased to have today Peter Kuchment from Texas A&M University, who's going to talk on some analytic problems arising in spectral theory of periodic elliptic operators. Thank you.
First of all, I want to thank the organizer for inviting me. Cambridge Newton Institute are my favorite places. So I don't travel much nowadays, but I cannot resist temptation when I invited here. Now, first of all, the problems I will present two problems. They are essentially about more or less several complex variables. I can formulate them such that you won't know that it has any relation to spectral theory. But actually they come from spectral theory, and that's why I will show first where they come from. These are two problems. One of them I've been looking at for decades unsuccessfully, and I asked all experts. Nothing happened. I have a strange feeling now that I have solved it in the last several days. I checked it twice, but I decided not to check it the third time not to find error before. And the second, also I looked at it for quite a few years, and I don't know what happens there. So let's first of all justify my presence at this program. Everything that I will be discussing comes from the spectral theory of periodic elliptic operators in Rn, or in more general cases, but Rn is difficult enough already. And so we have a periodic elliptic operator, usually of order 2. People in the area know that higher order operators have some issues, but they're less interesting. And the main example is the Schrödinger operator with electric potential, although all those things can be done, or at least formulated for more general periodic elliptic operators. So we introduce the complex vector K called quasi-momentum, and we commute our operator with multiplication by this exponential e to the power ikx. The reason is very simple, that if you have a periodic operator, you have to do harmonic analysis like for periodic functions. You have to expand in Fourier series. That's why you do this. So if you commute, you get operators that depends now on this quasi-momentum. And I will restrict this operator on the torus, since the coefficients are periodic. So instead of one operator in the whole space, we have family of operators dependent polynomially on K on the torus. In particular, if for the Schrödinger operator, that's explicit formula how it looks like. It's quadratic pencil of operators. Now, it is well known that the spectrum of the original operator in the whole space is the union of spectra for all quasi-momenta, real quasi-momenta, of operators h of k. Since h of k are elliptic operators on the torus, the spectrum is discrete. So in other words, you have, for each k, you have a discrete set of eigenvalues, and then when k changes, they start sliding. And so what happens, you have those so-called bands. For instance, this is the range of the lowest eigenvalue. This is how the second eigenvalue changes with k, the third, etc. They can overlap. I just draw them so you can see. Sometimes they overlap, sometimes they leave open bands and open gaps. So this is a famous band gap structure of periodic operators. now I'm interested in the so-called Bloch variety, and I have many of those on me shown. So if you graph the spectrum, so again, we just discovered that the spectrum of the operator S is a union of values of spectra of H of k. Geometrically, it means that if you draw the graph of spectrum of H of k, so here we have k, this is the plane of k, over each k you draw the spectrum, discrete spectrum, and then k varies, and this draws this beautiful picture, which is called in physics dispersion relation, and mathematicians like the name Bloch variety. So again, all drawn on my t-shirts are Bloch varieties of different operators. And so, in other words, what was said before means that if you have this picture, you project it onto the lambda vertical axis, and whatever it covers is a spectrum. In particular, here you see that you might have a gap, spectral gap. Nothing will be covered. Bloch varieties can look very complicated, but they always tell you something. For instance, for the free operator, just Laplacian, this is just parabolic shape. But there could be very interesting features. For instance, here, in this case, you see there is a flat thing. All of those can be interpreted, and I will not do this. It will move me a little bit away from my topics. So what is important that this Bloch variety, it can be proven that it is a set of zeros of an entire function of k and lambda of finite exponential type, which means that there is this estimate in this function like absolute value f of what was lambda k doesn't exceed constant e to the power constant absolute value of k lambda to a certain power p bigger than 1. So it is not an obvious fact. Essentially, it is done as follows, that if these were operators h of k were just finite dimensional matrices, you would take determinant, and it would be the set of zeros of the determinant. Here you need to use regularized determinants for operators of Schatten-Einman class. I will not, it's irrelevant. What is important for me is that there is an entire function, and it grows with such an estimate. And this estimate is true for all complex k and lambda. Now, if you can include this potential as a parameter as well, and then the same is true. So you can consider function. There is an entire function of all variables, including the Banach space, appropriate Banach space of potentials, which is entire in this infinite dimensional space and also has the same kind of estimate. Certainly, potential also enters here. Okay. So now, another notion is a Fermi surface. What is a Fermi surface? It's just a level set of the dispersion relation. So what you do, you fix some values, eigenvalue lambda that you want, and you look at the set of all quasi-momenta for which it is eigenvalue in the spectrum. And those Fermi surfaces can look very complicated. You have several of them drawn. And in physics, there are the whole books devoted to just albums of Fermi surfaces. The reason is that they tell you a lot about the behavior of physical properties of the material. So for us, this is just a level set of Bloch variety. In particular, one can notice that since the spectrum is the projection of Bloch variety on lambda axis, but only for real quasi-momenta, you can determine from this that also I will not need to use it, that spectrum happens when you don't have real Fermi surface, where there's this section is sitting somewhere in complex plane, where there will have gap. Okay. So these are my main objects here. And I will address two questions. One about generic properties. What do I mean by this? Suppose you want to have some nice property of your operator. And you know that you expect that it would be kind of the generic situation. At least you want it to be generic. So this means that unless you are in very bad luck, this nice property holds. What it means? It means that, for instance, in the space of potentials, you want to prove that almost all potentials are nice. I will tell you in what sense, for instance. Almost all potentials are nice. So this is kind of Arnold ideology about looking at generic case. So non-generic cases that would appear probably when you start changing your potential. For instance, sometimes you would hit those non-generic cases, but generically things are good. So what are examples of those properties that we want? For instance, non-degeneracy of extrema. Let me go back and explain on the picture. So if you look at this picture, you see the spectral gap here. And what are the edges of the spectral gap? Clearly from the picture, these are extrema of Bloch variety. Extremal. And you want to know whether it is true that unless you are in really bad luck or very special situation, those extrema look parabolic, which means that they are non-degenerate, isolated extrema. In physics, it's very important observation, since if it happens at the spectral, at the boundary of spectral gap, and if this extremum is parabolic, this means that if you don't go far, solutions should feel like they are in the free space. And this is in solid physics. This means that electrons would behave, if you're not too far from this position, would behave as free electrons. However, the only difference is that parabolic shape doesn't have to be round. It could be different. It could have different widths in different directions, which leads to funny things, that those electrons feel like free, except that in different directions they have different masses. So that's what physically means. So you want to know, for instance, is it generically true that extrema of dispersion relation, extrema of those Bloch varieties, are non-degenerate? It's known to be not always true. You just look at some pictures that I showed, or you will see cases when it doesn't happen. It doesn't have to happen, for instance, for magnetic potentials. There are examples, but generically you want it to be true. So effective masses, which physicists use constantly, they know that it is not always correct. They exactly understand this, but it's almost always correct. So this is one of the questions that I want to ask, whether extreme are generically non-degenerate. Besides effective masses, this study of the structure of the extremum is important for many other things, for homogenization near this extremum, for Green's function asymptotics. Even if it's not a simple extreme, for instance, if it's flattened a little bit, it influences the behavior asymptotics of Green function. It influences what kind of Liouville type theorems you have. It influences limiting absorption, etc. So I will not get into this. This is just propaganda to tell you that it is about spectral theory. Another thing is, another question which looks completely esoteric, at least it used to look till the recent years, irreducibility of Bloch and Fermi varieties. What does it mean, irreducibility? Those varieties are sets of zeros of entire functions. They are analytic sets. But imagine that your analytic function can be non-trivially factored into product of two analytic functions. Then the set of zeros of the product is the union of sets of zeros of one and another. And those two functions usually normally know nothing about each other. So this is so-called reducible set. When you can factor non-trivially, and so those sets of zeros split into two components that have no clue about each other. What does it mean have no clue? Another way to formulate it is that if you exclude all sets of zeros, definitely have non-smooth points. If you throw away all smooth points, or non-smooth points, you only keep the smooth points of your variety. Irreducibility means that it is connected set. Since the ideology is a very simple fact that, not that trivial to prove, but the idea is very simple, that if you have two functions that don't know about each other, take their product, take their zeros, you have two sets of zeros, and they cross each other somewhere. If you remove those crossing, the remaining parts will be disconnected. So that's one of the view of reducibility. And there is conjecture that I will talk a little bit about this, that Bloch and Fermi surfaces under appropriate circumstances should be generically irreducible. Well, who cares about this? Irreducibility of Bloch variety, first of all, it's much stronger property, and that's why much harder to prove than absence of pure point spectrum. It automatically excludes pure point spectrum for a very simple reason, that if you have pure point spectrum, Bloch variety has a flat plane at lambda at pure point spectrum. And this flat piece definitely is separate component. So it's reducible. But there are much simpler way to prove absence of pure point spectrum. But there is an ideological thing, that if Bloch variety is irreducible, it means that if you know your dispersion relation lambda of k nearby a point fixed lambda and fixed k, it determines uniquely the whole world. So you cannot change anything else. If it's irreducible, if you know this little piece of some values of quasi-momentum and little near some lambda, you know everything for all lambda and k. It is very interesting regions. Well, about Fermi surfaces, again, I told you that one of the immediate implications of reducibility is absence of pure point spectrum, but you can prove it much cheaper. With Fermi surfaces, it's more interesting. It is reducibility of Fermi surfaces popped up. Actually, people have looked at this a little bit almost 30 years ago for discrete cases. In the book, Giesecker, Knorrer, and Trubowitz, they looked at this, but it was not clear for what is the reason. But in about 20 or 25 years ago, in our paper with Boris Weinberg, we discovered sudden relation. So when you look at perturbation of your operator, localized perturbation, you add to your periodic potential something that vanishes very quickly or even compactly supported. We know that this can introduce pure point spectrum. The question is, can this pure point spectrum sit inside of previous absolute continuous spectrum in the interior or not? This thing has been solved 50 years ago, at least, for 1D. And there were no results at all about this. And now we understood why. Since we proved that if Fermi surface is irreducible at some lambda, you cannot embed eigenvalues.
So what would you mean cannot? By localized perturbation?
What?
By localized perturbation of the potential?
For instance, I have lambda in the inside of absolutely continuous spectrum of V. I add localized perturbation. Can it happen that this perturbed eigenvalue, pure point spectrum, which can arise, can sit at this lambda? The answer is no, if Fermi surface is irreducible. So then after that, many people jumped on this bandwagon and tried to prove irreducibility. It's in this case, I want to say that Fermi surface depends on which lambda you cross. You don't expect it all to be always irreducible, but the claim is except a discrete set of lambdas, it's irreducible. So there are only, it's very interesting, there are only very special lambdas where you could possibly introduce pure spectrum by adding localized potential. Physically, localized potential would be you put wrong atom somewhere. So now, so my goal is to see about genericity of these two properties. When can you expect that things are, unless you are extremely unlikely of probability 0, you have those properties. Okay. Any questions so far? Okay. Now, the first step is the following. All those bad sets we don't want them, are sets of zeros of entire functions of finite exponential orders that I wrote. And I want to know, so these are bad values. Now, let us project, for instance, on the set of potentials only, V. This set of zeros is in space of quasi-momental lambda potentials. Let's project the set on potentials. You want to say that this projection is either almost nothing, that's what we want, or almost everything. How is it helpful? If it's almost nothing, and suppose you found a potential near which you can prove that everything is fine, then you conclude that everything is fine almost everywhere. So almost nothing or almost everything in terms of bare category. So either the projection of this set is residual or its complement is residual. That's a conjecture. That's a conjecture. And this, you see, I didn't want to start with this problem since you would ask, what the heck does it do with spectral theory problem? Now it's naturally pops up. So this is the first step for proving genericity. And there is a nice case which is constantly used. Look, this is only the first step. If you prove that your set is either residual or is complemented residual, then you need to find a good point in the neighborhoods of which you can prove that either everything is everywhere holds in this neighborhood, or at least in the residual set of this neighborhood. So this is only the first step. The hard step after that to work with specific potentials, to find good potential such that it works. But this first step happens to be already problematic. In the case of discrete operators, everything is algebraic. All functions are polynomial. And in this case, there is no issue. Since the set of zeros of algebraic over polynomial is algebraic set, and there is famous theorem, there are several theorems of this type, like Zeidenberg-Tarski, for instance, that the projection of algebraic set is semi-algebraic set. Semi-algebraic means that given not only with algebraic equalities, but also inequalities, you exclude some parts. Then it's immediately clear that either it's almost everything, either it's the whole thing but an algebraic subset, or the other way around. That's it. But it doesn't make even the discrete case simple, since the main thing after that, which usually involves algebraic geometry, to find good point where you can prove that it is residual near this point. But this is the important first step. However, we are dealing with analytic sets of zeros of analytic functions. Unfortunately, such a theorem, that projection of a set of zeros of analytic function is either residual or complementary residual, is wrong. There are very simple counterexamples in C2. Okay, our functions not just analytics, they are entire. It doesn't help. It's harder to provide examples, but still, it's not true for the sets of zeros of analytic functions. However, if you have analytic functions with this kind of growth, it's seemingly true. And the whole thing started exactly 100 years ago, so it's appropriate year today, when Julia proved this in C2, that if you have analytic set of zeros of such kind of analytic function projected on C1, then it's either residual or complementary. Then it had to wait for a long time, and in 1986, I don't know, maybe he proved this a little bit later, it is in the famous Lelong and Grumman book on entire functions. It's proven for any dimension, but unfortunately, only projection on codimension 1. For our purpose, it doesn't work, since we always project along bigger dimensions. Oh, you can say, why don't you iterate? Doesn't work. Since after you project it once, the projection is much worse than the original set. You cannot do the next step. Now, you see, hopefully, it looks like after fighting for many years, just in the last several days, it looks like I have proven this in any dimension, in any dimension for any codimension. So the removal of the codimension 1 condition in the long theorem. I checked it twice, and I didn't want to check third time to discover error before my presentation. So I will keep checking. Since I fought with this for such a long time unsuccessfully, and I contacted all people involved in such things. But it looks like that I have proven this, so hopefully that's the word. Moreover, if my proof works here, it looks like it should work for infinite dimensional case. There shouldn't be much of a difference, and we need infinite dimensional case since we project on spaces of potentials. But even with finite dimensional case, it is useful since imagine that you have family of potentials depending on finitely many parameters. Then you have finite dimensional case. So this is what I know about this first question. So the first question again was, if you have in finite and infinite dimensional complex space entire function with this kind of estimate, take its set of zeros and project on a subspace of finite codimension. The whole dimension could be infinite, finite codimension. Can you prove that it's either residual or complement is residual? So this is the state of affairs as far as I know. So you see, it's exactly 100 years from Julia. So it would be nice if I don't find there. So that's essentially it about the first problem, about genericity. Any questions here? So, if there is none, then let me go to the other one. Which is about irreducibility. I have already formulated what irreducible means, and the conjecture is that at least for Schrödinger operators, I don't know about more general periodic elliptic operators of second order, it's expected that a Bloch variety is irreducible. Irreducibility is, and it was proven in the rather famous paper by Knorer and Trubowitz in 90. The proof was difficult, complicated. How those things are done, for instance, in algebraic cases, when you have algebraic variety, you go to compactification, to infinity, and you check there whether there is any reducibility, which is easier usually. However, this thing of compactification that works well in algebraic geometry doesn't work in analytic case. But Knorer and Trubowitz found a version of this compactification at infinity that works. But it is still open in other dimensions.
Is there a difference between dimensions? So in other words, is it expected that irreducibility is more likely at higher dimension?
I have no clue.
What?
I have no clue. I don't know. So I know people attempting, including myself, proving this, and we were failing, but expectation is that it probably should be correct. But I will mention a different approach in a minute. There are many results in discrete cases. For instance, first results in the book by Giesecker, Knorer, and Trubowitz, there are many recent results by young mathematician Winsai Liu, and they all use algebraicity very significantly. Some of them use the tricks of compactification of those algebraic varieties and go to infinity, or some other tricks, but they are not working for the PDs.
The graph Laplacian.
Oh yeah, discrete case means you have, let's say you have not necessarily Laplacian, but you have periodic graph, periodic with respect to the lattice Dn, and Laplacian, and plus some periodic potential.
In one-dimensional case, you have a class of finite gap operators. Is it known for them?
You mean whether what is known
Irreducibility,
for finite? Yeah.
because these are algebraic.
I don't think it has anything to do. The issue is that in 1D, gaps play significant role. For instance, if you know the gaps, you know the potential. In higher dimensions, gaps don't have any significance. The bands overlap, and you might have no gaps at all. For instance, in 1D, if you have no gaps, the potential is 0. It's not true for higher dimensions, for discrete or continuous, since for a small potential there are no gaps. But there is an analog of this, so-called Borg theorem. The Borg theorem in 1D, it's equivalent to claim of that if there are no gaps, the potential is 0. The Borg theorem is that if you have your block variety, and if you have an entire function whose graph sitting completely in the block variety, remember block variety is the graph of multiple valued functions, this weird graph. If you have an entire function whose graph sits inside, then it is just pure Laplacian. And in 1D, it's very easy to check through those, we know how the dispersion relation behaves near the bad ends. It's equivalent to absence of gaps. So the correct version in higher dimensions is existence of entire section. Now, this was proven not long ago by the same Winsai Liu in discrete case. This is geometric Borg theorem. So this is not spectral theorem, it's geometric. It's not about the spectrum, it's about having nice analytic non-singular section of this block variety, of this complicated singular variety. And it looks like very recently it was proven in continuous case, but I am not about to disclose. This is not, I've seen work where apparently it's done correctly and beautifully, but hopefully it will appear soon.
You mean the solution to the open in general?
What?
You mean the full solution to the first statement there?
No, it's not. I was answering the question about Borg theorem. So the analog, geometric analog of Borg theorem, that if there is analytic sanction in the block variety, then potential is 0. It is proven, but it's not about reducibility. And not about reducibility, I don't know any progress in this direction. So now here is my second question is about the following approach. So you see, if you have if you have an analytic function, a scalar analytic function, whose the set of zeros is reducible, you can prove that you can factor this function. It's reducible since there are two factors that don't know about each other. Now, if you recall the very first slide, I don't want to go back, that our operator, depending on k and lambda, is a polynomial operator pencil. You remember k squared, that actually quadratic pencil of operators. And now you want to know whether the set where this operator is not invertible is reducible. That's exactly a block variety in the previous incarnation. But the operator is not, let's say it's matrix operator. The matrices are not invertible when the determinant is 0. So if you take determinant of this operator, pencil, and look at its zeros and try to see whether it's reducible. Or equivalently, if you take this determinant, it has, you check whether it has factorization. Since if it's reducible, you can factor. It's not obvious. It's non-trivial theorems that if you have matrix pencil, polynomial matrix pencil, and the set of its zeros of determinant is reducible, that you can factor those matrix. It's not obvious, but it's true. I don't know, it should have been known since Euclid times, but I don't know, the first place I know it was proven is here. There is a theorem which allows you to say that if you have such a polynomial matrix pencil and its set of its degeneracy is reducible, you can factor it into polynomial pencils. Okay. But it's for matrices. Our operators are PDEs. So there is no determinant. What saves us is that you can use so-called regularized determinants, infinite determinants, for operators of Schatten-Neyman class. Essentially what you do, you have polynomial pencil like we have, and you take the leading term and invert it. Then you get polynomial 1 plus, and the lower order terms are Schatten-Neyman class operators. And so there is a determinant that does this. Well, this determinant is not a polynomial anymore. You can expect it. If you take determinants of very bigger and bigger matrices, it quits to be polynomial. So but they are entire functions with growth like this. And so now we can look at the reducibility as follows. We have this operator pencil, and the set of degenerates is reducible. Then, looking at matrix situation, you expect that there should be non-trivial factorization. And maybe you can try to do calculation and show that there is no factorization. It will prove inversibility. Well, there is one problem here. Those matrix and operator polynomials, for scalar polynomials, if you factor into polynomials of smaller degree. So if you have quadratic polynomial like we have, if it's scalar polynomial, you factor into two linear polynomials. However, when you deal with matrices of inverse operators, in matrices there are zero dividers. Two non-zero matrices can give you zero product. And therefore, if your matrix polynomial could be quadratic, but it can't, factorization could be into polynomials much higher degree, which doesn't happen in scalar case. And this is the issue. I can prove that there is no factorization of our quadratic operator pencil into linear factors. Unfortunately, it doesn't prove irreducibility. That maybe it can be factored into polynomials of higher order, and I have no clue what to do with this. So this is the issue as where kind of I stuck. It seems to be a nicer way than to do what is in discrete case. In discrete case, you take those determinants. They could be polynomials of very high degree, and you go to infinity, etc. It's a lot of hassle. Here it should end up very simple algebraic calculation about factorization. But this fact that factorization of matrices is non-unique, that there are zero dividers, screws everything up. So I can prove that there are no linear factorization. In scalar case, it would be the end of the story. But maybe there is factorization, non-trivial factorization to higher order polynomials, and then I don't get anything. So this is such an attempt to have a different approach to proving irreducibility. You exclude factorization. And I couldn't yet. I only could exclude, even for operator quadratic polynomials, only of specific times that comes from Schrödinger operator. I can prove that you cannot factor into linear. But maybe I can factor into quadratic and cubic. I don't know. Well, and so that's what I have already said, that I was excited that I can prove that there are no linear factorizations, but I don't know what to say about absence of any factorization. It's probably a very hard problem, and it's kind of reminiscent of things that people have studied in algebraic geometry. It's matrix factorization of polynomials. What it means is you have scalar polynomial P of z. Now you put matrix with diagonals. On diagonals is P of z, and then you try to factor this matrix polynomial. And the whole hell breaks loose there. It's not completely understood question, and what is understood I don't understand. It's above my head. So it looks like, well, there is warning sign. It looks like I found some examples where there is no linear factorization, not for quadratic polynomials of our types, but in general, some quadratic polynomials that there is no linear, but there is higher order factorization. So I don't know. This is still up in there. And now, thank you.
So any questions?
If you had a reducible block variety, is there any implication for the operator that it came from originally? Is there anything?
If you have reducible?
If the block variety is reducible, so one of the non-generic cases, what you're proposing is a non-generic case, is there any implication for the operator? Factorization doesn't seem to be quite the right thing. But
I'm not sure this way, but I definitely know how to create reducible Bloch-head Fermi varieties. So, and this is related to the last thing I was saying. First of all, essentially it would mean that you have two hidden operators. Two operators that don't talk to each other. And this happens, for instance, in waveguides. In waveguides, you have different transversal modes. You can put one operator on one mode and another on another. Another way, it means that you have direct sum of two different operators. But this is not a very good, for instance, for Fermi surfaces, there are examples of reducible ones where this doesn't happen, it's still reducible. Since it is incorrect understanding of reducibility. Understanding of reducibility is multiplicative. So if you have this thing, you can write the operator, if this is A, this is B, you can write it as A identity times identity B. But there are examples of reducible Fermi surfaces where it's not sum of two operators, but it is product of two operators. So this is a product of two operators, that don't know about each other. They are not of this form. But that still produces irreducibility. And in particular, about embedded eigenvalues, this essentially means, actually, the irreducibility is not required. What is required is that if there are several reducible components, they all show up in real space. There is no such thing that one component is real space. There is hidden component over there. What we actually need is that all components show up here. Since what happens essentially, like in waveguides, there are two operators. They don't know about each other. So for instance, in waveguides, you can easily embed eigenvalue for one mode inside of the spectrum of another mode. So that's essentially everything I can say. So more is known about Fermi surfaces. That's all about Fermi surfaces. For Bloch varieties, I don't know. The conjecture is that for Schrödinger, it's always irreducible. But so essentially the idea, if it's reducible, there are two operators acting that don't know about each other. And you can play strange things. For instance, take spectrum over there and embed into spectrum here. So that's just all I can say.
Yeah.
So, is there any result for, let's say, in 2 dimension, where the periodicity is in 1 dimension and the potential is localized in the other direction? In other words, Floquet operator. Any result?
Actually, those things have been considered. It's something like waveguide. There are papers studying the cases when you have periodicity in this direction and compact support on that. They were studied like this. Not about irreducibility, but already the spectral study is pretty tricky.
The first property on the extreme values of the Bloch varieties, does it say anything about the multiplicity of the eigenvalues?
It doesn't have to say. It's not about multiplicity. Multiplicity arises when you have two sheets of block variety touching each other. But suppose it's simple eigenvalue. So you have only this maximal shape. But how it is shaped, what is the first term of expansion here, tells you everything you want to know about many things, about how the Green's function behaves, Liouville theorems, homogenization near this edge, and all, everything else. But it's not about multiplicity. The conjecture is, and generically, this extremum is simple, isolated, and non-degenerate. But if it's isolated and degenerate, it will also tell you, if you know exactly how degenerate it is, you can tell a lot about Green's function and all those things.
Any more questions? Okay, thank you, Peter, again.